Alrighty, so 12.3 will be the study of these things called geometric sequences. Last week we talked about arithmetic sequences. Let's sort of refresh our memories on those. So the idea is that number patterns sequences in general are very difficult to describe, to figure out, because it's all about being able to recognize patterns. There is no um, blueprint to sequences. It isn't you do this every single time. It's intuition, it's gut feeling, it's experience, with the exception of simple, super duper easy patterns. One of those patterns that we discussed last week are called arithmetic sequences, and the idea is that arithmetic sequences are number patterns formed by repeated addition of the same number. So if your number patterns is constantly adding the same number over and over and over again, we call it arithmetic. Contrast that with geometric. Geometric sequences are number patterns that are formed by repeated multiplication of the same number. I think that's a very easy concept that everyone can wrap their minds around. Oh, if I ask you, hey, just make up a simple pattern, I'm pretty sure most of us will either make a pattern where you're just constantly adding or you're constantly multiplying. If you're constantly adding something, it's called arithmetic. If you're constantly multiplying something, we call it geometric. So that's all we're going to talk about today. Now, just like with arithmetic sequences, because the behavior is so simple and predictable, there are formulas and equations that describe number patterns that fit into this category. So let's talk about the definition of a geometric sequence. So the idea is that a geometric sequence is a sequence, no duh, of the form you start with some number, any number, right? And then you're going to be constantly multiplying it by a number. Now, the letter that we typically use for the thing you're multiplying by is r for ratio. So the very next term is that same number times r, and the very next number you just multiply by r again, so it's r squared. The next number you multiply by r again, so it's r cubed. The next number you multiply by r again is r to the fourth, and so on, and so on, and so forth. So any geometric sequence that follows this pattern will be represented in this way. The idea is that the nth term of the sequence, that is to say the formula, may be written as, so here's the formula for a geometric sequence. A sub n is equal to a sub 1 times r to the n minus 1. So that is the formula to find a specific term of an arithmetic sequence. Notice it's raised to the n minus 1 because you actually don't apply the multiply by r, I should use lowercase, you don't actually apply the multiplication by r until the second term, so you always have one less r's as term numbers. Just for completeness sake, let's go ahead and define all these variables, even though they're pretty straightforward, where a sub 1 is the first term, r is what we call the common ratio, the thing you are multiplying by. The reason why they call it common ratio is because you have to use division to figure out what it is you're multiplying by if it's not obvious. The common ratio is always going to be any term divided by the previous term. Hence, that's why we call it ratio. And n, of course, is the term number. So, I mean, it should be a pretty straightforward idea. It's just like arithmetic. If you know for a fact something is geometric, you can pretty much go on autopilot because it's guaranteed, the sequence is guaranteed to follow this pattern, to follow this behavior. So, for example, if you were asked, find the nth term and the 8th term of 5, 15, 45, 135, so on, and so forth. Now again, just like with last week, you sort of have to pretend that this isn't 12.3 a geometric sequence. Before you apply any formulas, you have to verify or confirm that it is geometric to use the geometric formula, or as last week, you have to confirm that it is arithmetic before you can use arithmetic formulas. Now in this particular instance, it should be pretty obvious. I think the numbers are simple enough that everyone can pick up the pattern. The pattern should be times 3, right? Times 3, times 3, times 3. Now let's pretend that you didn't know that. Let's pretend that you couldn't see that. Remember the definition of R. You can always find out what R is. Well, let's use a different color. You can always find out what R is by just picking two numbers that are next to each other. It really doesn't matter what two numbers. Let's say these two numbers here. R is always going to be the number divided by its former number. The right number divided by the left number. So in this case, it's always going to be 45 divided by 15, which gives us 3. So all this work tells us that R is 3. So to find the nth term, that is to say to find the formula, I need R, which we have, and I need the first term. Well, if they list it out, we can just see that a sub 1 is 5. So we're done, right? So the nth term, I guess I'll do this, a sub n is simply a sub 1 times r to the n minus 1. That's it. Easy peasy. And then to find the 8th term, just plug in 8 for n. It's 3 to the 8 minus 1. And that's going to be a pretty big number. So you'll go ahead and pop out your calculator, do 3 to the 7th power, that answer, times 5, and you're going to get 10,935. So there is your 8th term. Easy peasy. Right, so. Yeah, that's sort of the idea. If you know it's a special sequence, if you know it's arithmetic or geometric, you should be relieved. It should be simple because we have formulas to help us. Now, the next example is a very classic sequence example. I sort of tipped my hand last week when we did arithmetic. It's when you're given two sets of terms. So, for example, what if they told you the third term of a geometric sequence is 63/4, and the sixth term is 1701 over 32. Find the fifth term. So again, this is a classic setup when they give you just two random terms that calls for normally systems of equations. So they tell you that the third term is 63 over 4. Symbolically, they tell you that a sub 3 is 63 over 4. The idea is that you should be able to translate that into an equation because they tell us it's geometric. So because they tell us it's geometric, that geometric equation is unlocked, and then we know that the term number, the term value, 63/4, is equal to the first term, which we don't know, times r, which we don't know, raised to the n minus 1. Now they tell us that it's the third term, so n is 3, right? 3 minus 1. And similarly, you can do it to the other information. The sixth term is 1701/32. Symbolically is a sub 6 equals 1701/32. And the idea is that you can translate that into an equation. And then you can solve this system of equations. Now this is a system of non-linear equations because you have exponential expressions in there. But the idea, the technique is you take these two equations, divide them out so the a sub 1 cancels, and then you can solve for r. That is the standard way of doing it, and that's the traditional way of doing it, and it's a perfectly fine method. But just like with arithmetic sequence, if you understand the structure, if you understand the logic of it, we don't need to do this. You can just think it through. So what information did they give? And that's what that's the technique or the method I'm going to show in this video. What information or what terms did they give us? They gave us the third term, and they gave us the sixth term, right? And I know for a fact the third term is 63/4, and I know the sixth term is 1701/32. Now this isn't arithmetic, so I'm not repeated adding. This is geometric. So the idea is that from the third to the fourth term, I'm timesing by some r. Fourth to the fifth, I'm timesing by r. Fifth and the sixth, I'm timesing by r. Now in this particular example, it was easy enough where I could just count. I can clearly count that there are 3 r's in between 3 and 6. But just like with the logic technique with arithmetic, the idea is that the number of r's between 3 and 6 is 6 minus 3. Right. Now you have to remember that this is geometric. So these r's are all multiplying each other. They're not adding each other. So this is r times r times r, or in other words, r cubed. This logic says I know for a fact there is an r cubed that's separating the third term from the sixth term. So we just write that out as an equation. If I start at the third term, 63/4, and I multiply by r cubed, because we said there were 3 factors r in between, I should end up with the sixth term, 1701/32. So this should give you a way to solve for r, right? You divide both sides. I guess I'll show my work. Divide both sides by 63/4. You get r cubed equals, do some fancy math. The 4 and the 32 reduces to an 8. The 1701 and the 63 reduces to 27. So that's 27/8. And then you go ahead and take the cube root of both sides. R equals 3/2. Now typically the idea is once you solve for r, you plug it back into one of these equations to solve for a sub 1, and if the instructions did say, hey, find the nth term, that's exactly what I'd do. But since they said to find the fifth term, I'm just going to go straight to finding the fifth term. Now to find the fifth term, you just need a known value, and we have 2 of them, the third term and the sixth term. It doesn't really matter which one you use. I'm going to use the sixth term because it's closer. So what's the logic? The logic is, and remember sequences, they go in order, so you have to write the fifth term first. Between the fifth term and the sixth term, I don't know what the fifth term is, so I'll use a variable. I do know what the sixth term is 1701/32, and the idea is that there's only 1 r separating the two. So if I start with the fifth term and I multiply by r, which we just figured out, right, that's 3/2, I should end up with the sixth term, which is 1701/32. Therefore, to solve for a sub 5, you divide both sides, or multiply both sides by the reciprocal of 2/3, and if you multiply both sides by the reciprocal of 2/3, you're going to get Let's see, 32 divided by 2, so that's 16 on the bottom, and 17.1 divided by 3 is what? That's 5, carry the 2, so that's going to be 5, 6, 7. There we go. So it's the same types of problems that you saw last week with arithmetic, except we're going to tweak the logic a bit. The pattern, the sequence, is not repeated addition anymore. The sequence, if it is geometric, is repeated multiplication. So sequences, if the pattern is simple, they're easy to do because they are predictable. Have at it. Good luck.